Thanks for the invitation. It's always pleasure to be here. I have always been benefited whenever I come to TIFR. Okay, so I am going to talk about Chern-Simons theory on 3 manifolds and matrix models. So roughly this is the goal. Recently we have started working on this thing and we made some progress, but still we are working on few questions which still are not clear to us. So, we are working on those points, but roughly this is the goal. Write down the partition function for CS theory on 3 manifold in terms of quantities in W Weisdumino-Witten models as a sum over integrable representations. By quantities in Weisdumino-Witten model, I simply mean that modular transformation matrices. I will come to those transformation matrices and their properties as I will go along. So, using the properties of modular transformation matrices, we express this partition function as a unitary matrix model. And I will show that discretization of eigenvalues appears naturally as I mean all these things I am going to tell you, and eigenvalues are proportional to Hooke numbers of a Young diagram corresponding to some integrable representations. And then the study of large n phases, which Siraj has already, Siraj and his collaborators, they have already studied long back. So, I will look at those large n phases, but from a different perspective, from the perspective of dominant integrable representations. And we will see that the level rank duality and transposition of large n representations will be manifest when I do it in this way. We will revisit Chern-Simons partition functions, Chern-Simons theory on S3 and write down the partition function as a unitary matrix model. There are some issues we still do not understand very clearly. I want to discuss those things with you. And we also observe that one can cook up a 2 gap phase and if possible maybe some multi gap phase in Chern-Simons theory on S3, which has same free energy as 1 gap phase. So, there are some issues in Chern-Simons theories on S3 which we still have to understand in more detail, but I want to discuss those things with you. So, before I go to
just to get context, the localization people have some sort of matrix representation of the S3 partition function.
Right.
Will you land up on the same thing?
I will land up on the same thing. So, this is basically Siraj's work in 2013. So, this is the partition function Chern-Simons on S2 cross S1 coupled with matter. You integrate over matter fields and you go to large n limit. In the partition function you write as a matrix model with some effective potential. Effective potential depends on what kind of matter field you are considering. Matter fields are in fundamental representations and U is the holonomy. And one can also show that the UN fluxes basically discretizes the eigenvalues of these holonomy matrices. So, this is the eigenvalues of holonomy matrices. The discretization is 2 pi by k plus n. Here my k is bare level. Okay. And
I should know this, but matter is massive or conformal?
Matter is in the fundamental representations.
That VU.
VU. That contains all the information about the.
I mean, the zero modes on the S2 for the matter.
The zero modes on the S2 for the matter, even if it's conformal, the S2 gives it a mass.
Okay, just from the.
See, apart from the A0 mode, all other modes are massive. So, you can integrate over out. So, this U is basically the A0 mode.
Thank you.
Okay. Okay. So, although the phase diagram is quantitatively same for other matter fields also, but let us take Gauss-Witten-Wardia model where the when the potential is this ratio plus ratio dagger. Integral over mu is the matter fields. Okay. So, this is the phase structure. Beta 1 beta 1 is the coupling constant sitting here.
It is like the temperature?
No, beta 1 is not the temperature. Yeah, okay, right. Yeah. So, you have a temperature term okay, which goes as square root n. So, the whole thing I have clubbed at n times beta 1.
So beta 1 is the scale version of the temperature.
Scale version of right. Okay, so it has 4 phases, no gap phase where the eigenvalues are distributed on from minus pi to plus pi. Lower gap phase, there is a gap in the eigenvalue distribution. Upper cap phase, there is a eigenvalue is, so it's not clear, 1 over 2 pi, eigenvalue density is 1 over 2 pi by lambda, 2 pi lambda, and there is a cap gap phase. So, these are 4 phases, and also one can show that the Gauss-Witten model, Gauss-Witten-Wadia model is self dual because trace un goes to trace un under transposition. So, cap
So this was made as model corresponds to particular some theory.
this is just a toy model. This is just a toy model. Okay. So, since it is self dual, what happens that the lower gap phase is level rank dual to the upper cap phase. Okay. So, this is the work done by Shiraz and his called Shiraz, Sochin and other people.
Including spent.
Including sorry. Okay, and of course, it's a old result that eigenvalues are like positions of free fermions. There is some underlying fermionic picture for a given unitary, not just unitary matrix model, even for Hermitian matrix model, and these eigenvalues are like position of these free fermions.
Sorry, you said it, but I understand the gapped and the ungapped, but what are the additional 2 phases?
This is the no gap phase,
No gap phase.
and this is a gap and with a cap. They are level rank dual to itself.
Gap with it?
This is a cap here, and also there is a gap here.
What does gap mean? Sorry.
Cap means eigenvalue saturates 1 over 2 pi lambda.
That was the point. Okay, I got it. Yes.
So, cap means eigenvalue saturates 1 over 2 pi. Okay, maybe I should mention it here because that is something I will need. So, cap, when I say cap means eigenvalue saturates this upper bound, which is 1 over 2 pi lambda.
Right. And that was because of the statistics. So, what was your story?
The simplest way, I'll quickly say that. The simplest way is that suppose you take Chern-Simons theory and you think of e to the power I k, that's I k A0f. Now you sum over fluxes. The sum over fluxes force A0 to be discrete. In units, the discretization units are 2 pi by 2. Okay. Now, because of the van der Waals measure, no two eigenvalues can sit at exactly the same point. Normally that doesn't matter because the eigenvalues become very near when they push. Because the eigenvalues are now discrete, if no two eigenvalues can sit at exactly the same point, they have a maximum density. And that maximum density is what we're looking at.
Okay, good.
Okay.
So then, just to understand, so you have a cap up on the upper right hand side with a gap.
With a
and
gap.
Here in the lower right hand
There is a cap, no gap.
So that's why you get 4 possible.
That's why I get 4 possible.
And you have only one parameter, n beta 1?
Beta 1 is the one parameter and lambda 2 coupling is another parameter. Lambda is given by n by k plus n. So, you have 2 parameters, and in these parameters, so this is beta 1 axis, this is lambda axis, these are the phase boundaries.
You realize all 4 phases.
For this Gauss-Witten-Wadia model, you can exactly calculate eigenvalue distribution for all these 4 phases.
But what about our...
For any generic case, I think after that,
Yeah. It's basically a question of whether lambda is small or big. If lambda is small, you go from, you always start with the uniform kind of distribution. And always end at very large temperature with cap and cap.
That's the delta function.
That's the analog of the delta.
Yes.
Delta.
Yes. But you go through it either with a gap phase
or a cap phase, depending on how you are
Depending
going.
on where the lambda is
Yeah.
small, you go through, you get the gap phase. If lambda is large, you get the cap phase. You see, because caps are very hard to form when lambda is small, because the bound on eigenvalue density is very large. So when lambda is small, the cap doesn't easily happen.
This is less.
Yeah. But when lambda is big, that's more likely to happen than
Cap, yeah.
the other. So in this model, exactly at lambda equals half, you transit between the two.
lambda equals to half. Yeah.
Is this model some fundamental?
So when this BU is in terms of trace U plus trace U dagger, that means
One loop.
One maybe one.
One loop. Yeah.
yeah.
Maybe one loop. But even with any matter, there'll always be the full
Yeah.
series.
In general, I mean, if you take any matter, you can actually write, you can replace this potential by some kind of placket model, beta n trace U to the power n plus trace U dagger to the power n. Okay, and this beta n basically depends on whether you have fermions or bosons and all these things.
But though this is not realized with any matter, it's. I mean, you can analyze the actual models with the matter. It's more complicated, but this thing is exactly solvable and shows all the qualitative.
Right.
And
Yeah.
lambda is bosonic fermion. For example,
Lambda is bosonic fermion. Sorry.
lambda is 0 could be free fermions or free bosons.
Well, lambda is the
For this statement, it doesn't matter, and it's important that it doesn't matter that under duality, cap goes to gap.
So that was
Yes,
the
under duality cap goes to gap. Yeah.
Yeah. So every phase where the bosonic or fermionic and weak coupling in that regime,
In that lambda.
always has the gap phase, and that's consistent with duality because duality changes.
Duality is actually that of the Chern-Simons theory with probe
Yeah.
or
I think
dynamic
yeah.
matter.
I think that's in this case, this model is exactly.
sorry, so what the duality is level rank duality. Is the way I understand? For now this and levels just remind me what lambda under level rank goes to 1 over lambda.
1 minus lambda.
Oh,
In this
1
way,
minus
the way I have defined it, it goes as 1 minus lambda.
1 minus lambda.
So lambda ranges from 0 to 1, and yeah,
And that lambda is the same one.
this lambda is the same lambda. Yeah. In the there's a difference with Siraj's. Say here my k is the bare k. In your paper, it was the denormalized k plus n.
And that the lambda, the way you define it, which appears in 1 over lambda, can become
These lambdas are same. Lambdas are same.
bounded, right?
Yeah.
And
Lambda then becomes at most one.
At most 1.
But can go down to 0. So suppose lambda reaches 1, then your bound on eigenvalue densities is 1 by 2 pi. And then the only eigenvalue density that's allowed is 1 by 2 pi everywhere because it has to integrate to 1. So lambda 1 is forcing you to a very particular range.
Okay.
thank you.
Okay. So next, let me just review little bit this old paper. So unitary matrix model also has an interpretation in terms of in the language of free fermions with number of boxes in the Young diagram corresponding to different representations of un like momentum. Okay. So you given a representation, you have some distribution of boxes which I call u of hi's. Hi's are nothing but the hook numbers. It should be n I. Okay. And so therefore this ui's are like u of hi's are like momentum distribution, like rho theta is our position distribution for these fermions. So u hi's are like momentum distribution of these fermions. Basically you start with the same, let's say Gauss-Witten-Wadia model, okay, but this is true for any generic unitary matrix model. You use the Frobenius formula, okay, and write down the partition function as a sum over representations of unitary groups, okay, e to the power some function which depends on what representation you are considering. I am not going into showing you the exact expression for these in the right hand side because that is not exactly needed for this talk.
In general, your partition function involves only traces. You are using that fact and writing the same quantity in terms
So
of
some-
characters of different representations.
In terms of characters of different representations, right.
So the Gauss-Witten model you are now replacing the trace U.
No, I am not
Or you
replacing
put
the
up
trace u,
trace
but so for Gauss-Witten-Wadia model I have, let's say, trace u. For same thing we will go through for trace u dagger part. This you can write trace u to the power n over factorial n, okay, sum over n. Okay. So this quantity you can write sum over r chi r of k1 okay, times some trace R of U. So chi is the character of the symmetry group.
And in general, you will have a sum over this.
Sum over all sum over representation of Un.
Yes, but in particular, suppose you are taking a representation, fixed representation R there,
Right, where? Here?
in the above line.
Here.
Then here you will have.
Here all everything is in fundamental, is a n by n representation.
Yes,
So this is
here
what
you are starting with fundamental. So when you write in the character formula, you could have written in general n, like not taking into account large n.
this is true for any n, right?
But are you going to do simplifications using large n?
Right. After you write this e to the power trace u and then e to the power trace u dagger, you write in this way, okay, and then you do some simplification, then you land up with some results. If you want, I can exactly show you what exactly the result.
Is that finite n? So far you have not taken large n right now.
See, at this point, I haven't taken any large n limit. Okay, if you want the exact expression, I can do it for you.
What is vector K?
K. Oh, K is the K's are the cycles. K vectors are K1, K2, and some Kn and so on. So this chi R of K is the character of a conjugacy class in representation R with K1 number of 1 cycles, K2 number of 2 cycles, and so on.
So it labels the young tableau.
Labels the young tableau. Yeah. R labels the young tableau. K1 K vector labels the conjugacy class.
Conjugacy class of the group element.
Conjugacy group.
Group element. Wait,
No. Sorry. Conjugacy. So I am dealing with a representation R, which has total number of box n Kn. This is the total number of box. Let's say R.
Is chi R K is a character of the unitary group?
No.
Or the symmetric?
Symmetry group.
Okay, now I understand, I think.
Symmetry group.
Yes.
Well, now I'm a little sorry to be very K does not label a particular conjugacy class in the representation R.
No. K represents the conjugacy class of the symmetry group.
Symmetric.
Okay.
Which is
See-
different from that.
Right. See what exactly I am doing. This is
Number of particles with
right. So what I am. This is my Frobenius formula. Okay. So you multiply chi R is du, okay, trace R of u dagger and then that factor. You multiply this with trace R prime of u. Okay. You multiply with trace R prime of u. Okay, and if you do the integration, what you will land up with this expression, whatever that is there in this bracket, this equals to sum over R chi R of K trace R of u.
Let me try to say this. Yeah. You see, there's this character polynomial. Given any representation, you can rewrite the trace of the group element in that representation as a polynomial in traces of the same group element in the fundamental representation.
Right.
Okay. For instance, in the adjoint, it will be sort of like trace u times trace u dagger minus 1. Symmetric. You know, that's the kind of thing. Now, suppose you've got a representation with n boxes. The character polynomial could have many kinds of things. It could have trace u to the 5. It could have trace u4 times trace u. It could have trace u squared, and so on. So now what he's written there is a particular kind of monomial in the character polynomial. Right? He's fixed some number of trace u's to the power k.
Right.
And what he's getting is the coefficient of the expansion
Will give you
of
the
chi r in this monomial.
which are nothing but the characters of
Which
the symmetry.
happen to be the characters
Example
of
is represents symmetry group.
Okay, so it's like
I got it. Okay, so now just to understand, take the representation R, take the character of a particular group element, then you expand it as trace of U, where U stands for
So
that
by
group
this-
element
this-
in the
this-
fundamental, right?
exactly.
These traces are in the
This false,
fundamental.
and this gives you the
Right.
And it's a complicated polynomial because you could have trace of u cubed.
Exactly. This trace is in the fundamental.
Yeah.
This trace is in the fundamental.
But I should think of this bracket as coming down from an exponent.
This bracket is basically coming down from the exponent.
That's what I was saying. The earlier slide, if you take this gross Witten model and
Gauss-Seidel in Gauss-Seidel-Navier model, your K2, K3, K everything is G.
Can you go back to yeah, in this Gauss-Seidel-Navier model, we have trace U. Instead of that, if you write trace U in some representation R prime,
Oh, okay.
then that R prime would have admit this character polynomial decomposition,
Oh,
which when you bring down would produce this.
okay. So you are asking here this trace U is in the fundamental.
No, not here it's in
Fundamental.
But
If you some other R prime, okay, then probably you have to write the similar formula for that.
then the factors that then that would be re-expressed in
Re-ex-
terms of fundamental trace U.
Right,
which
exactly.
as
Right,
Shah said.
exactly.
And then as you bring them down, you will precisely get.
Right. Yeah.
So there's a way to obtain it through an exponential.
Yeah, I think this would mean if you have some field, let's say some representation, not fundamental, some other representation, then this is the kind of matrix model we use.
Okay. Okay. So in the large n limit, again, so this is the same partition function, but now written in terms of sum over all possible representations. In the large n limit, what happens that a particular representation will dominate the partition function. Okay. And in this paper and some previous papers, we showed that Young diagrams distribution actually works as the momentum distribution, which I have already told you.
You also define f of r.
Oh, f of r. Okay. So, well, it depends if I take, well,
So you take this
if you-
contribution of a particular r.
no, f of r,
and exponential.
yeah, f of r depends on your, I started with this matrix model. Okay, f of r depends on what v u I am considering. Okay, if I take, it is simple, if I take v u to be just Gauss-Seidel-Navier, then it is simple. Otherwise, you can write given whatever u, v u written as a function of defined powers of trace u n, okay, you can write f of your f of r.
I mean, I understand you can bring them down, write it as sum over r, but now that you can exponentiate it back.
You can exponentiate it back, right? Yeah.
As a function.
Yeah.
What is your last sentence? When you said it, I remember, because momentum is a continuous variable, right?
Momentum is a continuous.
Particular young tabulous, and this is all discrete information.
Yes.
So I was not sure.
So I mean, when I go to large n limit, what happens then? This becomes continuous variables. Yeah. Yeah. I will also tell you so a little bit more why these HIs are like momentum. I will.
I haven't understood f of r either. One of you could explain.
Okay. So should I?
If you don't mind, because it's probably important.
So let's just do it for Gauss-Seidel-Navier.
Yeah.
Okay. So I have du e to the power. Let's just take trace of u. That's it. Okay. It's not yeah, some beta 1 trace of u. So what I do, du beta 1 to the power n factorial n trace u to the power n.
Right.
Okay. This trace u to the power n, trace u to the power n is nothing but chi r of k1 trace r of u. Okay. Plug it here. Okay, actually I need both beta 1 trace u dagger. I need both. So I will have beta 1 to the power n plus m factorial m trace u dagger.
Now
To
I
the-
understand.
now we
is
are-
it right that you take the trace u part, the part that's just from you, and write it as a sum over characters?
Write as a sum over
And then
character.
you take the trace u dagger part and write it as
Sum
sum
over
over conjugate
conjugate
character and conjugate character click, and the clicking of
by character you mean this
Yes,
this
yes.
character. Okay.
Conjugate character click, and whatever that is called a e to the power.
Right. Right. So same thing you do it here. So same thing for you do it here.
Yeah, what I was missing was the trace u dagger, because I was not understanding how you got non-zero.
Yeah, and also you have a r here. Similarly for trace u dagger you will get something r prime some, and then you have a du. So you have to use du trace r of u trace r prime of u dagger will give me delta r prime.
And where is the discretization of the eigenvalues put in?
Discretization of eigenvalues.
This is just for pure unitary matrix model.
This is pure unitary
This
matrix.
is not yet with the Chern-Simons effect. No lambda at this point.
No lambda here.
Yeah?
Right now there is no lambda here. I will come to lambda. I will come to lambda.
Yeah, okay, good.
Okay. So now what we observed, so okay, so given this matrix model, you solve what is your, in the large n limit, you solve what is your dominant representation. Basically you find u as a function of h, like in eigenvalue case, in eigenvalue picture you find rho as a function of theta, how eigenvalues are distributed. Here I find how boxes are distributed in the large n representations. Okay, you
H will be some particular representation?
h of u is some h of u in the large n limit, one particular representation will dominate this partition function, okay, and you solve the saddle point equation and find what that dominant representation is, means what this function is, is a function of what that function is. So this particular pattern will dominate my partition function in the large n limit.
U as a function of h is the length of the hth row.
U as a function, u of h is nothing but minus del x del h. So in the large n limit I have hi, I discretize it, is n times h of x. Okay, this is my x is I by n, x is I by n. Okay, I go to the continuum limit, I define this is my continuous variable given a hi, and this is what my eigenvalue Young diagram distribution function is.
Okay. Sorry, now what exactly is h in the Young tabular?
hi is ni plus n minus I. Ni's are the number of boxes in the ith row. Hi's are called hook lengths. Hook lengths.
UH is sort of like the distribution of hook length?
UH is sort of distribution of hook length, which is same. If you know UH, you know UN.
Something that parameterizes how many, the length of the ith row. Right?
Length of the ith row, exactly.
Some combination.
Yes.
And then you are not finding more than one saddle point, because in row theta variables for Gauss-Witten-Wadia there are these competing phases, right?
Oh, here also you will find that. Here also you will find that depending on if you change your parameter beta 1 less than half, you have one possible dominant representation, beta 1 greater than half, just to our Gauss-Witten-Wadia, not Gauss-Witten-Wadia or Chern-Simons. You have for beta 1 less than half, you have one dominant representation, beta 1 greater than half, there is another dominant representation. So, yeah, that same thing you will find here also. Okay. What interesting is that we found a relation between the eigenvalue distribution and the Young diagram distribution. Okay. And this is the relation. This is the relation. Okay. H plus H minus are the maximum number of hooks and minimum number of hooks. Okay. What we had shown that this relation is kind of generic for any unitary matrix model.
So in all this you are taking V of u to be arbitrary.
V of u to be arbitrary, yes. Okay, so that is what our observation in some other paper.
And this u of h depends on
U of h depends on exactly what your V of h, and of course it is in the large n limit. So given the potential, U of h will tell you, you give me some values of parameter, I will tell you which representation will dominate the partition.
For just V of u linear, trace plus trace u dagger, how does it look like?
For just Gauss-Witten-Wadia model, for beta less than half, you know, beta for Gauss-Witten-Wadia model, beta 1 equals to half, there is a phase transition from gap to no gap. Beta less than half, no gap, beta greater than half, one gap. So beta less than half for no gap, eigenvalue distributions are like this. Okay, finite fraction of rows are empty, and for beta greater than half, it's like this, all the rows are filled. Okay, this is like Douglas-Kazakov phase transition, okay, in the 2D Young-Mill site. Okay.
So sorry, just to ask, this is just a statement about matrices, is it, in the large n limit? That is,
This statement is in
large n matrix with a particular eigenvalue distribution.
this
translated into how hooks are distributed.
right, that
This will be true.
right, this relation is in the large n limit, yeah, this relation is in the large n limit.
But I mean, it's just a statement about matrices, right?
Just statement of matrices. How the eigenvalues are distributed in the eigenvalue side or in the Young diagram side, how boxes are distributed, and we find a relation between them.
Very interesting. And then just to understand, this is true, and you already said it, but just to ask, true no matter whether you are in the ungapped phase, ungapped, or gapped, or gapped cap, this is always true.
This is always true. This is, I just take a matrix model, any unitary matrix model. I took the matrix model, I took VU e to the u, and this VU I have written some beta n trace u n plus trace u dagger n sum over n from 1 to infinity.
Wait, but at this point there's no lambda.
Here there is no lambda.
Nothing, no, but I'm just saying this is just a statement about matrices, right? If the eigenvalues are distributed like this, and that
This
seems
is
to
like
be
computing the position and momentum of a Gaussian, right? Being them being related, because the eigenvalues would be like positions.
Eigenvalues are like
This is
position,
like,
momentum, yeah.
But,
Yeah.
But it's true regardless of whether you have a gap phase,
Well, just a clarification here, the Chern-Simons thing is not quite a matrix model. Right? It's a matrix model with the additional input that eigenvalues are discrete
Capped.
or capped. So this will not by itself apply to the Chern-Simons.
Now I will. Up to this point there is no Chern-Simon. It's just a unitary
Old
matrix model.
matrix model.
Old matrix model, right.
this map you expect a priori, right?
This map I expect.
Yeah. Or not?
This map we derived actually for any generic unitary matrix
Not
model.
expected a priori.
I do not know. We found this actually one can derive from the you take that particular some arbitrary unitary matrix model and you can do it.
At small value of beta 1, you have sort of uniform distribution.
If at small value of beta 1 I have sort of uniform distribution.
So your row-
Well, actually at beta 1 equals to 0 I have a uniform distribution.
Yes, that's what I like. Around 0. So near 0 you have a uniform distribution. So your rho theta is almost like a constant.
Okay, so let's say at beta 1 equals to 0. Okay, yeah, I have a uniform distribution which corresponds to no box.
Uniform distribution, that means h plus minus h minus is
It's very small, very small. H plus minus h minus. If your beta 1 is very close to 0, your rho is almost well uniform. Yeah, h plus minus h minus is kind of uniform.
Yes.
Okay, so h plus minus h minus kind of uniform means it's kind of this.
Yeah, so the low values of beta 1 is this picture, and the left one, the one that
This is for beta 1 less than half, and this is for beta 1 greater than half.
When you say low beta 1, you mean low temperature.
yeah, beta 1 is like temperature.
Low temperature.
So his low beta 1 is like low temperature. Then you have uniform distribution in eigenvalue distribution. And I'm trying to understand his mapping.
I think in the situation where you have almost no temperature, there should be almost no excitation.
Yes.
So you know his thing is this, right? It's the dominant singlet is coming from taking fundamentals and making complicated representations, taking anti-fundamentals, also making a complicated representation, and then they're kicking.
Yes.
When you have very low temperature, you would expect the dominant representation just to be identity.
I mean, there no box.
Nothing.
Yeah.
No box.
Yeah.
In this side,
Yeah.
in this side,
Very small things are very small representations.
In his large n scale, it will be nothing.
nothing,
Yes.
You should get a young tattoo with nothing.
nothing.
Which
I think
Or-
that his thing will go
Or
up.
maybe basically this box, which is nothing.
Beta doesn't enter in this box. This formula.
Beta doesn't enter. Yes, okay. Well, yeah, beta will tell you I mean, depending on beta what is your h plus and h minus. Yeah, this relation. Yeah,
Plus h minus is not a function of theta, right?
h plus h minus. This is the identification. This is the identification.
Beta tells it what row of theta is.
What row of theta is.
But what is identity? This big one is identity. If I think about SU, and this
So identification is following. Identification is following. So
because this is mapping and information.
so I have a UH as a function of H. Okay. You write that, so it gives for this phase you get right hand side is kind of a quadratic function. Okay. invert this function. So, this for a given u of h, it has two roots, h plus and h minus. Okay. You take the difference between these two roots, which will turn out to be some function of u of h. Now, if you use this identification, pi u of h equals to theta, then this function will basically turn out to be rho theta. If you want, I can do the calculation for you explicitly. It's in our old paper. Okay, but let me just go ahead and just take this relation, this identification between the eigenvalue distribution and the Young diagram distribution. So, this is for a generic unitary matrix. Yes, sure, please.
Yeah, I just wanted to make sure I understood Shiraz's comment. This is a statement about matrices in the larger limit, etc. Then your point was Chern-Simons theory is not just a theory of matrices because of the discretization. Here, of course, he's assuming that you get continuous distributions in larger. That's what he meant.
Right. There's no, effectively in larger, there's no cap on the eigenvalue itself. Chern-Simons theory is same model but with that cap.
With that cap.
Okay.
So, now I am going to do the same analysis for Chern-Simons on S2 cos S1, which tells me that rho theta has a cap. So, which means h plus minus h minus by 2 pi must be less than equals to 1 over 2 pi lambda.
Right.
Okay. So, a constraint on eigenvalue density imposes a constraint on Young diagrams, and the constraint is for Chern-Simons matter theory on S2 cross S1, the dominant representations have Young diagram with maximum width, and h plus minus h minus, I am telling the maximum width to be less than equals to 1 over lambda. Okay, because you just rho theta is 1 over 2 pi lambda, so h plus minus h minus must be less than equals to 1 over lambda.
And what does that mean for the shape of the Young diagram? What is h plus minus h? I'm sorry, I don't have intuition for what h is.
H plus minus h minus is kind of this. I'm coming to that just in the next slide.
How much of a gradient?
Right. H minus is the minimum value of the hook. H plus is the maximum value of the hook.
Yeah, what my problem is I don't have intuition for these hooks.
Okay. Okay.
Can I ask you, because Abhijit made this statement, which is roughly h is conjugate to theta, is it? That's
H of u, u of h I thought is conjugate to.
H of u is like momentum distribution. So, if I have some underlying fermions moving in this potential Vu, so H of u, rho of theta are like position distribution of these fermions, which is well known.
yeah.
U of h is like momentum distribution for these fermions. And
Like individual Young diagrams.
momentas are like hooks of that individual Young diagrams, right?
In this picture, which one has larger h plus minus h minus?
This is this length corresponds to h plus. This is not h plus because this is h plus is the hook length. You have to use this relation. Okay.
Between these two pictures, which one has larger h plus minus h minus?
H minus here is 0.
Okay.
H plus is something non-trivial. H plus, this is my h minus here. Okay. This I am calling h minus because this point corresponds to I equals to n. I equals to n means h n equals to n n. So, this length whatever is, this is n of n, this is nothing but my h minus, the minimum value of the
And the
hook.
upper one is h plus?
Upper one is n1. What is n1? So, h plus is n1 plus n minus 1, you can ignore in the minus 1. Okay.
Sorry, I mean you said u of h is like momentum distribution, but that means h is like momentum.
H is like momentum. Yeah, it will be clear. I will tell you something interesting.
That's why the spread is also going.
Yes.
So for small lambda, you will get, first you will go through.
No, don't go to lambda. Right? Yeah. Okay.
First you will go through the left one.
Last I go to the left one. What is the left
For
one? Sorry.
example,
Oh, I'll come to the phase space. Okay. So now what I have to do, like eigenvalue. So given this constant on rho theta, what you do, you solve the saddle point equation in presence of that constant. Here also I have to solve the saddle point equations in presence of the constant that the width cannot be greater than 1 over lambda. And you can find all the Lagrange representations. I am not going to derive all those Lagrange representations. That is not the goal of my talk. Okay.
Sorry, the fine know what the constraints of rho of theta, that the eigenvalues become discrete. So there should be a finite n characterization on what does that translate to some finite n statement about what representations can and cannot appear in this sum?
The finite n case.
Something like that.
Yeah, probably yes. But what we did, these identifications are at large n. Okay, maybe it's true. Okay, no, what does that mean? Okay, as I
larger representation doesn't mean anything for Chern-Simons, right?
let's see. That is what I am going to. Tell you. So you see, since we are dealing with representations of un, okay, a diagram with non-zero h minus is same as, I can just throw this part out, okay, same as a diagram with 0 h minus. Okay. So it's like that. So I have a non-zero h minus. This diagram is equivalent to this diagram.
This is when it's maximal.
This is the maximal, yeah.
You just throw out all the maximum.
If it is not maximum for this diagram, my h minus is anyway 0.
So for un, these two diagrams are different, right?
Yeah, you can take conjugation of this diagram. So conjugation of any diagram is same. So if you take conjugation of this diagram, we will get this diagram.
Maybe the u1 charges of the two diagrams are different.
That's what I thought, but he said that it would work anyway.
So sorry, say again.
Is this truncation happening only when, are you throwing away only columns of length n?
Only columns of length n. Yeah. Only columns of length n. Yeah.
Sorry, but if the Chern-Simons is SUN at level 3.
Here there is no like affine algebras. Here my theories, I am considering the partition function I am writing sum over representations of un only. So all these representations I am getting, these are the representations of un. It's all the
Chern-Simons, you should write it as sum over integrable.
That's what I am coming. So this means h plus must be less than or equals to 1 over n, 1 over lambda, which essentially means n1, all the large n representations I am getting in the Chern-Simons theory, n1 should be less than or equals to k plus 1. N1 is the number of blocks in the first row. This is nothing but the integrability condition. Okay. So although as I was telling, although we are dealing with representations of un, but somehow we see that the dominant representation will fit as integration representations of unk.
It's still not any large n.
Yeah, we are in the large n limit.
What you're seeing, I think what you're seeing is just the fusion rules of the Western. When you do this integral u, but with the discretization, you generate the fusion rules not of SUN, but of the Weissmuller way. I think that's what you're seeing. That what you're doing is taking these trace u's and multiplying many of them and representing them as some character.
Right.
And then you're saying that only the integrable representation.
Because I have finite number of primary. Yeah.
More generally, you're seeing the fusion rules of the algebra.
Okay.
So it's not just the truncation.
Okay.
The singlets that will be formed are not only from R and R prime, delta R prime, but also R plus K, right? Some equivalence classes.
But in this statement that you see the integral representations is not restricted to large n.
Yeah, I think
So
it's fine.
this will probably go through.
Yeah, this is integrable representations are for finite n also, but
This dominance you are saying, you said you are taking into large n into account, but this statement that at the end you get only integral representation looks like valid modular.
yeah, I mean if integrable representation are defined for any n, any k. Yeah.
But when you take the fusion rules of Weissmuller theory, then only representations that are allowed are those integrable.
Here what we are doing, I have written the partition function in this form, and I see that in the large n limit, those diagrams will dominate the partition functions which are kind of integrable which will fit in the integrable representations of unk.
Yeah. But I think that Indraji is saying that more is true. If you take chi r1 of u times chi r2 of u with this integral over u plus the discretization.
Okay.
That is the same as inserting a sum over chi r's,
Okay.
where the r's that you get come from the fusion rules of Wesson-Witten theory.
Okay. Huh?
I think that's just a general identity.
Okay. It's possible.
So you can do that one by one.
Okay.
Do it to all the u's, do it to all the u daggers, and then hit.
Oh, okay. Yeah, that is, yeah.
Visualization also at finite and you get this the same thing. This black sectors give you this sum, right?
Yes.
Because of that.
Right. Sum over r e to the power f of r. Without loss of generality, that should be truncated, right?
That should be truncated in the sense,
Integrable representation.
but
Because when you do this
but
integral,
when I use this, this sum is for any r of u of n.
But so that r labeling is meaningful if r and r conjugate r click, right? But
This
now with the discretization, many things will start clicking, right?
Exactly.
R and r plus a longer one will also click with r.
Right.
So in that sense, the true label is just smaller r.
You know,
And then once you do that, you take large n, you are bound to get this kind of thing.
Yeah, I think what you are telling, that is something I am going to see the same thing. So this is just from our earlier analysis, and honestly speaking, we are not much familiar with this integrable representation.
Actually, I have one suggestion. These are 3 of 18, so maybe we should
Last time I had 25 slides and I couldn't finish. So this time I had 18 slides. Okay, so now, so just huh?
It's actually 36
Yeah. Okay. So, so what we have seen that, maybe I can skip some slides. So the large in the large n limit, no gap and lower gap phases fit in the integrable representations of u n k. Okay. The cap gap, upper cap phase will fit in the integrable representation of u k n. And this is something I would like to tell you, say, because we are telling about h to be the momentum of the underlying fermions. You see, when my eigenvalues are discretized, that means my position space is discretized, latticized. When I do that, what does that mean? The corresponding momentum is periodic. What is the discretization? 2 pi by k plus n. So the corresponding momentum should be periodic. So momentum should range from 0 to k plus n, which is exactly 8 the limit condition on h what I am getting. So this is kind of the first Brillouin zone. Okay. Now let me just flash it. So one can draw some phase space picture, Wigner distribution for different phases of Chern-Simons theory on S2 cross S1, but it has nothing to do with the current talk. Okay. Now let me go to the Chern-Simons theory. So this is the Chern-Simons theory with label k, rank n. The action is it's a topological, doesn't depend, nothing depends on metric. The observables are the Wilson lines. Okay, and the partition function and the observables are just the expectation values of these Wilson lines. Okay, in this, so we will consider a special case. The manifold, we will take some Riemann genus G Riemann surface times S1, and the gauge group is UN. The expectation value of Wilson loops, okay, Wilson loops in different R1, R2, Rn representations can be written as a sum over integrable representations. Okay, times something and some S R 0 R. So these S zeros are nothing but the modular transform matrix, which makes the affine characters. So you do some modular transformation inversion, tau goes to 1 over tau, and then this matrices basically mixes the affine characters of this affine
This is
diagram.
a complicated way of writing the fusion rules, right? Or maybe a simple way of writing the fusion.
Well, yeah,
You're just fusing R1, R2, R3, Rn and counting the number of signets.
random signature, right?
But using Wesson, and you're using
Berlinde formula, yeah. So see, here the sum over representations are over integrable representations, okay, and R equals to 0 corresponds to identity representations. Okay. So we thought that if I write a matrix model for this quantity, I will see all these large n representations. Okay. So just to, so before I write down the explicit expression for these modular transformation matrices, let me just very quickly write down the Gauss-Witten-Wadia model in terms of this Wess-Jumino-Witten data. So this is my Gauss-Witten-Wadia model. In the large n limit is the expectation value of this trace U plus trace U dagger. Sorry?
6, 8.
Oh, this is because I write this slide later and otherwise I have to change all these 18 to 19. So roughly 20 slides, not more than that, don't worry. Okay, so you do some algebra and you can show that the Gauss-Witten partition function, Gauss-Witten-Wadia partition function you can write in terms of these Wess-Jumino-Witten quantities in Wess-Jumino-Witten models. Now in this paper, Nakulich he showed that the level rank under level rank duality.
That went too fast. What have you done on the left hand side?
So I have just expanded it.
But how did you couple U to A? U is the holonomy of A or what?
U is the holonomy of A. Okay. So this is just Gauss-Witten-Wadia. So I expanded it and then I used this formula.
Yeah.
And then
S2 times S1 or
this is on S2 times S1. Yeah. This formula is valid for well, not this formula. This formula is for S2 cross S1. Yeah.
Basically, you're getting the fusion rules, the number of fusion rules for n
Insertions.
n fundamentals and n algebra. Number, you're counting number of conformal blocks of n fundamentals and algebra.
You didn't use large into this, right?
At this point, no, I haven't used large n. This is exact. Okay. When I write down the matrix model, I will go to the large n and find the dominant representations. So under level rank duality, this is what shown by Nakulich et al. S tilde is the same quantity for the dual representation. R tilde is the transposition. Okay, then you can show that these are the things you can prove, and you can show that Gauss-Witten-Wadia is self dual. Okay, just from the proper.
What was the expectation value of
S tilde, no, S tilde is the modular transform. Okay.
Got it.
Okay. So you can here you can show the self duality just using the properties of these modular transformation matrices.
So GWW self dual, you mean on the left hand side, GWW coupled
Right.
to Chern-Simons or
Chern-Simons coupled to GWW.
that is self.
Yeah.
Two expressions, two partition functions, one for the area and its level rank dual, and the two answers are the same. That's
Two answers, or do you need two
the
answers?
last line, summation over the representations.
Right.
There is a similar summation over representation.
Summation over R tilde, yeah, dual theory which is same. Yeah. Yeah. Of course, your beta has to transform accordingly. Yeah.
All the
Beta 1.
parameters
Yeah.
are
Yeah.
set.
Yeah.
Slightly observable question. Is there a quick way to see the level rank?
Not a quick way. I can tell you the Nakulich paper. It's not a quick way. Yeah, it's not a quick way. They used refined modular transformation parameters and came to this.
So there is no
Maybe there is, but at least Nakulich paper I didn't understand anything. Is there any quick way to see this result?
Very nice.
Okay, so now let me just very briefly tell you this story. So this is any matter theory. As I said, any matter theory you can write as a placket model. Okay.
But by the way, everything in your previous slide, as Anthony asked, could be done at finite.
This is everything can be done at finite n.
So if you define the Gauss-Witten-Wadia matrix model to be sum over discretized eigenvalues rather than integral, then that as an exact statement is the same at lambda and 1 minus lambda.
Right. So now you have a matter.
That gives you
Sorry, I didn't quite understand the. Can you go back to the previous? So S tilde is what you said?
S tilde modular transformation matrix.
Oh, the S is the modular transformation. The tilde stands for the level rank dual.
Dual thing. Yeah, tilde transforms the dual thing.
So that's just okay.
That between
I
the
thought
dual
dual
representation.
No, dual tilde transforms the dual thing. Yeah. Okay, so this is just whether you take fundamental fermions or fundamental bosons, you can write down the matrix model in terms of placket model. Beta n's depends on whether you are considering bosons or fermions. You do little bit of algebra. This partition function you can also write. Huh?
To get the first effective action, you already assume large n.
Large n, yes.
First line depends on large n.
First line depends on large n. first line itself depends on large n.
But then if you think of it as a statement about matrix model, then it becomes exact.
Yes, then it is very powerful.
Yeah, the first line itself is large n. Yeah. So you do some algebra, and then at the end you can show that the matter, Chern-Simons matter, you can write in terms of datas of modular transform matrices, and you can again try to check whether the level rank duality using the properties of these modular transform matrices under level rank transformation. Okay.
And what is the answer? It is level rank, isn't it?
No, the fundamental boson goes to critical fermions and then all these things. Yeah.
Criticality itself, etc.
So these are given by betains.
So there is you get a map between a beta and a beta theta now?
Yes, I haven't for this thing I haven't checked. For this thing I haven't checked. We are actually trying to check this result.
That's an added check of the dualities then, I suppose.
Yeah, so it's very closely related to the check that we had in our paper, because we also had the section, right? which
Yes.
said that
Yeah.
now once you've got the matrix model, can we use level rank duality to ask what property of the two matrix models will guarantee that they're the same?
Right.
Sounds very similar to it.
Similar to that.
What
Yeah.
is the relation between the criticality and criticality? What's the
Oh no, once you've written it as a matrix model,
okay?
suppose you've got two different matter Chern-Simons theories which you've translated into matrix model.
No, but this matrix is parameterized by beta i's.
Beta is, and one has a lambda and the other one has something else, one minus one. Then we ask what relationship should the first effective action have with the second effective action, so that the two partition functions will be.
Same. Yeah.
And the basic idea is to think of these as coming from effective Wilson lines, and so we worked that out. I think it's very.
And the beta is
Beta is mapped to some beta.
Some
something expected from
the
dual part. Yeah.
the-
Yeah.
Yeah.
the critical.
No, that works
Yes.
is a miracle. That works from Feynman diagrams is a miracle. So you use Feynman. All the hard work is you do Feynman diagrams and get this form.
Yes.
One calculation from the critical bosons, another calculation from the regular fermions. They're totally different calculations. But then, what property of these effective matrix models will make them
Yeah, that's
dual? That you can figure out quite easily.
right.
I think one
But that works is just a miracle.
Yeah.
one way of I mean, maybe I'm just making this statement. You can tell me whether I'm wrong or right. One way of proving this level rank duality, at least for large n, okay. Well, probably for that I have to take some supersymmetric matter, okay, and write the matrix model in terms of this data. And then I use the relation between use the properties of modular transform matrices under level rank duality. Will that be can I call that as a proof to level rank duality for Chern-Simons matter coupled to Chern-Simons theory coupled to defined matters? Here here at this step I have already taken that thing, large n limit, and then but if I can write, suppose I take some Chern-Simons theory with some supersymmetric matter, and by localization calculation I land up with this expression, and then I am using because this result, this is generic, it doesn't depend on any Chern-Simons or anything.
No, but that would be the proof of the supersymmetric version of it.
That would be the proof of supersymmetric
Why
version.
do you need supersymmetry for this?
For localization calculations, you need.
For say,
Exactly.
Here you do not need supersymmetry.
if you take your theory, non-supersymmetric theory, calculate this potential in large n. So you get the potential, you use large n, get the potential, and then.
But yeah, that is what I was asking. Can I?
Arbitrary operator insertion, let's say 4-point function, 6-point function. You take the large n calculation, you rewrite it in this way, and then use level rank duality. So then you.
Can I call it a proof? Can I call it a proof
For large n.
for large n?
Large n, I mean, it's fine. Even in large n, can you do it like if you have
So
4
that's what
operators
you
inserted?
say.
Yeah, for the partition function we more or less.
Yeah, for partition function,
for
let's say four
expectation.
operators inserted for 4-point function.
Then there will be more structure, right? Because you will have positions and so on. It won't
Yes,
be
so
just.
that is the question I'm asking. That these kind of things will go through for some.
It's not clear that it's just there's a matrix model and other stuff.
So and now you will have these parameters of insertions.
That's like
I'm
a
asking
block.
this question and I don't know the answer.
Sorry, you should go on, but just you folks identified the operator map also. the duality,
Yeah.
in general,
Well, yeah.
or at least for some operators.
The operators were
Very
sort of
much.
clear. Single trace operators was clear because they're the high spin currents operators. We are
Yeah, then you could do it, but it's probably much more complicated, right? There's so much more structure.
and then the position.
Yeah, because of that.
Yeah.
Okay, maybe
You go, but it's just, I didn't understand what you mean by Feynman diagram. I thought you folks identified the duality map for the coupling constants. So then, isn't it a matter of,
that's what I mean. Can I?
obtaining the potential for that choice of couplings, and then obtaining the potential in the dual discrete?
But how do you obtain the potential? You do that by summing Feynman maps. Because you have to integrate out the matter to get the effective action for the single.
Very specific values of beta I.
That's a very complicated calculation.
It's not just truncating down to some zero.
No. Integrate out. This is the thing that requires us to solve the differential equation, integral equation mapping. So this is a very complicated thing, and it requires, the two solutions look totally different until the end.
But if I do it for,
I understand what you're saying.
but if I can do it for some supersymmetric version, let's say
You are talking about the index.
index, yeah. I mean just using the localization calculation. Then
we get a proof of the equality of the indices. But we know the indices are equal. And people have proved that. So, anyway, my suggestion is finish your talk. We can discuss over that.
okay, so the modular transform matrices take this form. Okay, so I am considering UN. UN you can break in terms of SUN with level k, U1 with level n into k plus n, and modded by Zn. Okay, then UN modular transform matrices are written can be written in terms of modular transformation matrices for SUN. Okay, and this is the form of SUN. You do little bit, and this is det m, and det m is given by this. Okay, so punchline is that you do this algebra, you write down everything in terms of your Young diagrams, hook numbers. This is what S0R you will find. Okay. Now I go to matrix modular transformation matrix model. So let's take this prototype model. Okay. The summation over partition function is over integrable representation. Hook number ranges from 0 to k plus n. So since hook number ranges from 0 to k plus n, what I impose that I will impose a periodic condition on my hook numbers. Okay. And then I define these new variables theta I 2 pi by k plus n times h I. Okay. The periodicity on hook numbers tells me my theta i's are periodic between 0 and 2 pi. Okay. Then S0R square will have a factor which gives me sin square theta I minus theta j by 2, which is basically the measure factor for UN group. Sum over representations will be just sum over theta i's, and the partition function takes this form. Okay. And you can see that theta i's are discrete because h i's are integers. Theta i's are automatically discrete. Okay. So this whatever fluxes you said in your paper, these fluxes are nothing but the hook numbers. Right? This is your theta i's 2 pi by k plus n times n i's. Okay. So n i's are nothing but my h i's.
So summing over these h i's makes.
Summing over h i's means summing over theta i's.
Dominant flux sector.
So we see
The dominant flux sector is
here the sum over representations means sum over h i's, which is nothing but sum over eigenvalues. But the theta i's turns out to be proportional to h i's. H i's are integers. So in that sense, theta i's are discrete. In that sense, theta i's are discrete. Okay. So this is my Chern-Simons matter with, and all these things will sit in some function of thetas and k plus n. So and yeah, this is the Chern-Simons matter partition function. Now if I go to large n limit, let me take this particular example again. If I go to large n limit, this is my partition function. I take these continuous variables This is the partition function. Then I go from hi to theta variables. Okay. So you can see theta and if you write your effective functions, effective action in terms of thetas, and you do the saddle point analysis, exactly the same equation you will get. Okay. Only relation is that theta, rho theta is related to u of h. Rho theta gives nothing but the dominant representations. Okay. And you can see rho theta is less than 1 over 2 pi lambda, which means UH less than 1, which also is important because H is monotonically decreasing function. Okay. So then the story is well known.
Just one question. At low temperatures, at low temperatures. So at low beta 1, at small values of beta 1, this is supposed to be like sum over this trace gas of traces, right? So in this language, this the characters you will see will be coming only from representations corresponding to these higher spin operators.
Okay. No, I haven't thought in that way.
You know, the high spin operators are one fundamental, one anti-fundamental. The way he's thinking is what representations when you couple only the fundamentals, it's a different channel. You see, the way he's thinking is you take the u part, get the representations. Then the u bar part, get the representations, and then fuse.
Yes.
You're thinking, take one u bar.
Yeah, I'm thinking about one u bar.
U bar. So you're thinking like a cross channel.
Cross channel expansion.
Yeah.
Okay. So anyway, let me so this is the no gap phase, which corresponds to this dominant representation.
Well,
This is lower gap phase, which is 0. Now 0 in Young diagram distribution means there is a vertical line, sorry, horizontal line in the Young diagram distribution.
sorry, you could get arbitrary I mean, you could get something with 10 boxes, but 10 boxes on the other side, and then.
Yeah, but I thought he was claiming that only u bar could things down here.
But everything will in the end be polynomials in u. Oh, you mean not trace u squared?
Yeah.
That's what you're saying.
Only the first bracket, so more.
So what is it? Trace of u square? No.
Trace u dagger.
Oh, trace u dagger will be in the, yeah, you can
Same at low temperature, that should be dominant contribution.
trace
Coming
u.
from the fundamental. Is that what you're saying?
What is no sort of is that if you are low in low temperatures, there is this non-renormalization theorem for these higher spin operators. So you expect it's just this dimensions are not changing, so it's just the free energy that is coming from that.
And the highest
Those
operators are just pi bar with branch of derivatives.
branch of derivatives.
And the multi-particles.
Yeah, and
Tra-
particle of those.
Trace u dagger means you have adjoint matters, right? Trace u dagger means you have adjoint matters, right?
But given the multi-particles should be Bose exponential. Platistic. There's something to go from there to there. It
Not
may-
quite.
Yeah, not quite.
Sorry, I decoupled from their discussion. Okay, so as I said, 0 in the Young diagram distribution means a horizontal line in the Young diagram. Cap in UH or rho theta is proportional to UH. Cap in UH means a vertical line in the Young diagram. And for cap gap, I have a 0 and cap. So I have a horizontal line, then distribution, then I have a vertical line, then distribution, then I again have a horizontal line.
Wait, but sorry, and you said this, but cap means you reach the maximum row size.
Rho goes to 1 over 2 pi lambda.
No, that I know. But I mean, in terms of your Young tableau, you reach the maximum row. You hit the maximum row size.
No. When I do this mapping, when I do my cap rho theta less than 1 over 2 pi lambda is same as u less than 1.
And what does that mean for Young tableau?
So when rho saturates 1 over 2 pi lambda, u saturates 1.
What does that? Can you say, what kind of shape of Young tableau?
U saturates 1 means this vertical line.
Vertical line. Okay, and does it have to be at
No.
K?
No.
The upper part is doing that.
Yeah, that's why it's not at k. It's just going vertical at some order.
So here you can see here theta ranges from minus pi to plus pi, which means h ranges from 0 to 1 over lambda. So that is why here
Why does it go vertical?
why does it go vertical? What is UH? U of h is minus del x del h equals to 1. So h goes as x minus x. Okay.
Are you going to translate the rho theta? To
Right.
vertical?
No, not rho theta. I'm not trying to. I'm just telling you why UH equals to 1 corresponds to vertical line. Is that what you are asking?
No, I'm asking. It's a very strange kind of Young tableau, very non-analytic kind of Young tableau. I thought you were varying over all Young tableau so as to get so as to minimize the free energy or something.
Okay.
Normally you get these vertical things because of constraint.
Normally you get the vertical things because of constraint.
Like in rho of theta, you get this gap phase because there's a constraint. The rho of theta can't be less than 0.
Right.
Here there's no constraint in the neighborhood of this Young tableau.
Yeah.
Why is it going vertical?
So if you look at this diagram, okay, if you look at this diagram, okay, I think so. How does this diagram go to this diagram? There is a transition. Okay, so now you keep on increasing your beta, or sorry, you change your parameters. So at some points, so this is my diagram. So it will kind of like this, and then at some point there will be a kind of jump in the Young diagram. There will be a vertical line in the Young diagram when this eigenvalue or UH touches the upper bound. Rho theta touches 1 over 2 pi lambda means UH touches the upper bound.
Maybe what you're saying is that without the constraint, the actual thing would have been some smooth thing that would have exceeded.
Exceeded, exactly.
Now you want to not exceed and then find the best way.
Best way.
And so that makes you jump somewhere else.
Jump somewhere else. Yeah. So now this, as I said, these two phases are level rank dual to level rank dual to each other. So what?
So just to confirm, the end of that thing always hits end.
End of the thing always hits ends in this case. Yeah.
Yeah, sorry, always it's k. The row size of the upper region is always k.
Row size of the
Upper part of the Young tableau. The first row of the Young tableau, is it always k?
here it is always k.
Yeah. So then you have hit the bound.
Yes.
Okay, now it makes sense.
Yeah. So now what?
What? But can't you have a tableau where you don't reach k?
There is a tableau.
Yeah.
There is a tableau.
That is
Yeah, I think both these will not have reached k.
This has reached k. See, k reaches because theta goes from minus pi to plus pi. Theta goes from minus pi to plus pi.
But the lower gap phase doesn't see lambda at all.
Lower gap phase.
The low gap phase, for instance. You only see lambda when you have a cap.
Whether we reach k or n, the maximum row size is what? Sorry.
K.
See, this is my theta I equals to 2 pi hi by n plus k minus pi.
So just a general question. In a phase with no caps, the answer is the same as the Gross-Witten-Marjapane. It's independent of lambda. It doesn't know about k. So how can your tableau then know about k?
Well, if you do not know about k, then there is no constraint on this side.
Right.
So this is the diagram.
Yeah, but where is that length of that top row? Is it k or not?
The length of this one.
Yes. Is it less than k or is it k?
This is k.
Even in the no gap, even in a phase without a cap,
Yeah.
exactly what is bothering. It doesn't make somehow it doesn't sound right.
This is probably because of the see. This is my relation between theta I and hi's. Okay. Now if I say theta I equals to pi, so minus pi, which means hi equals to 0. If I say theta I equals to pi, okay, which means my hi equals to k plus n.
But I'm sorry, I haven't followed all the details of your thing, so I can't respond at this level of detail. But I'll just say again, in a phase without a cap, there is the answer to the problem is just that of the answer of the Gross-Witten-Marjapane model and is independent of lambda.
Independent of lambda.
So then how can it know about k? K is lambda, right?
K is lambda. So in this, if you do not have any, then why are you thinking about there will be a cut? It will reach somewhere.
It will reach somewhere.
It
It
will
will
reach
not
some.
k, right? For instance, suppose k was infinity.
Yeah, I think here I have used the fact that I am dealing with the integrable representations only. This input has gone into my
Suppose I take the
calculation.
weak coupling limit, k equals infinity. Will your tableau still go off to infinity in this no gap phase?
If you are in the weak coupling limit, k goes to infinity. Okay, so k goes to infinity means my lambda goes to 0. So lambda goes to 0 means yeah. So
but the answer to the problem is independent of k. So how can you say it goes up to k?
let me just think.
In a phase without a cap, the full eigenvalue distribution does not know about lambda. So how can it translate to some representation knowing about k?
Yeah, for k goes to infinity. Yeah, my hi. So for theta equals to pi, hi should also go to n plus k. Hi should also go to n plus k.
Yeah, I'll ask you later.
Yeah, maybe yeah, I will also. So now these two gaps are, as I said in the beginning, these two gaps are level rank dual to each other. So I expect that this diagram should be transposition of this diagram, but you can see it's not. So to see that the what exactly the relation between the Young diagrams, you can see that u of h under transposition goes like this. You can do the calculations, but let me just just tell you why this is so. So as I said, if you have a vertical line which corresponds to u equals to 1, when you take the transposition, it becomes a horizontal line, which means u equals to 0. So that is some reason you can understand that u of h goes to 1 minus u of h under transposition, but you can do the calculation.
Rho of theta goes to rho of pi minus theta. It is that.
It is something like that, yeah. So so now what my goal? I want to see how this diagram is related to this diagram. So as I said, my H space is periodic. So these are my Young diagrams. So I have stacked them periodically. Okay, and the diagram inside the red box is basically the diagram corresponding to lower gap phase.
This rule gives me the map from one representation to the level rank U representation.
This U, yeah, I'm telling you the mapping. I'm telling you the mapping.
In studying level rank duality, people know how to take a representation and map it to a dual representation. And this rule is very simple when n and k are both large and representation is fixed, but it's more complicated when all are complex.
Right. Yeah, okay. So this is the representation for lower gap phase. So if you want to see how this representation is related to the representation for the upper cap phase, what you do, you first shift the representation by h to, you change h by h goes to h plus 1 over 2 lambda. So which means you go from red distribution to the blue distribution, okay, and then you take a transposition. If you this is your phase, this is your representation for lower gap phase, you take a shift, you get this distribution, and then you take a transposition. If you take transposition of that diagram, you will get this one. Okay. So the mapping is basically u tilde, the distribution for the for the level rank dual phase is 1 minus u, but h replaced by h plus 1 over 2 lambda. These factors I have put because of normalization, because my u's are normalized. So if I integrate on both sides over h, so I should get both u and u tildes are normalized. So this is the relation between the u and u tilde, which will take you from one gap to one phase to another phase. If you perform the same exercise for no gap or cap gap phase, you can see that you will land up with the same type of diagrams. And this is actually similar to the rho theta. If you now use the relation between rho theta and u of h, you will get the same relation between rho theta. bit-
Now, of course, the dominant representation appears a certain number of times. It doesn't appear just once.
by certain number of time means.
Meaning, the dominant representation is dominant because it appears more times than anything else, right?
Right.
So somewhere along this, you're keeping track not just of that representation, but how many times it appears. When you do your partition function, you sum over representations and some numbers.
Yeah.
N of r's are also kept.
Right. Partition function goes as e to the power minus n square times something. Yeah.
Yes, you're keeping track of that.
Right. Right. Yeah. So yeah.
I mean, there's something you're extremizing, you can get the value of the thing.
Right. Exactly. Yeah. So
Not just where the extremize.
should I go there?
No, I'll just do whatever.
No. I mean, Chern-Simons on S3.
Sure.
Okay. So, Chern-Simons on S3 you can get partition function Chern-Simons on S3 from Chern-Simons on S2 by this surgery. So, what you do, you take a circle inside your S2 cross inside your S2. You consider a tube around that. This is the work by Witten. So, I am just telling the story from that paper. You consider a tube around that circle, you take the tube out and you perform two S transformations. First one will take the B cycle to A cycle to B cycle, and then the second one will take the B cycle to minus A cycle, and then you again put that tube back in S2. That will ultimately give you Chern-Simons on S3. So, if you
take Gauss-Witten over their model and do what you did on S2 plus S1 and do the same kind of similar.
no, this is pure Chern-Simons. This is pure Chern-Simons.
I know. So I'm asking if you have Gauss-Witten over there with this Chern-Simons fusion rules, and then you do the kind of thing that you did on S2 plus S1.
In this case, you are telling. I mean, this surgery you are talking about the surgery,
on S2 plus S1, you had an expression in terms of S matrices.
right?
So on
You can do the same thing.
On those S matrices, you can do
The
this
same
one
surgery.
modular transformation
Right.
to
See.
get some answer.
Right.
Is it going to be the same answer that you will get doing the same thing on S3? Because I'm asking this because now this is not topological anymore. To prove this identity,
This is topological.
for proving that Chern-Simons partition function on S3 is written as modular transformation of Chern-Simons partition function on S2 plus S1, certain things are needed. Like it's a topological thing that you are saying
Right,
that you cut it
right,
down 2 torus.
right,
that
right,
topologically
right,
torus,
yeah.
right? But if you have a theory which is not topological, for example, this Gauss-Witten model you had, if you do the transformation, nevertheless you will get some answer. Can you identify it by something in
No.
S3?
Well, I think one has to do. I don't
So
know.
all this happening is the level of pro matter fields, right?
Here there is no. Yeah, I mean, yeah. Okay. In this case, yeah,
Suppose that
yeah.
everything will work just like Chern-Simons with the insertion of some lines, and then everything will be in terms of S matrices. With the surgery, some additional insertions of S matrices perhaps.
Yes,
And
so
then,
it
things will
will
just
give
go
you some answer, right? If you
Yeah.
take the answer on S2 plus S1, do the modular transformation of S matrices, you get an answer. Okay? But if had it been a pure Chern-Simons theory, we know that that answer will be a particular way of writing S3 partition function of Chern-Simons theory. And now you have additional things. Can you still identify that? That's what I'm asking. On some theory.
So okay. So your question is on S3. If I have some additional insertion, can I write a partition function for that? Is that your question?
on first you take a
S2 is
you have an answer.
Right.
You do a modular transformation.
Right.
You get another
You
point.
should be. I think you should be able to write a partition function for this thing.
So
Yes.
you get an answer, keep it. Now, that answer, had it been a pure Chern-Simons theory, that would be, take that answer and multiply it.
Can
with
you
matrix.
discuss
Yes.
this after this talk? Okay. So the so this is for this answer you get for a particular modular transformation, but you can do a generic modular transformation involving both S and T. A particular case will give you this particular transformation, basically T, S and T transformation will give you this partition function. So these are something called framings. So these all these partition framings, all these partition functions, they are related by framings. Okay.
Not a length
Particular
space.
thing.
This is in a particular framing, right?
It's not a length space. SGS.
This is no, this is S3. No, this is the S. No, this is just S3. P equals to 1. Length space is P greater than 1. P 2, 3. Yeah. This is S3.
Not the Witten's framing, different framing.
This is Seifert framing. This is something called Seifert framing. This is called canonical framing. This is called Seifert framing. So, and T are same as S, but now your modular transformation is just translation, and these are the expressions for T. So, again, as I said, different partition function written in different framing, they are related to each other. You start from this, use the properties of S and T matrices, you can show that this partition function you can write, this partition function is same as this partition function up to some phase factors. Okay. You can check it for small gauge groups and small levels, you can do explicit calculation, you can check that there will be some phase factors. In the large n limit, what I will expect in the large n limit, only one particular representation will dominate the partition function, let us say r tilde. So, what I expect that in the large n limit, S square 0 r tilde times T inverse r tilde should be equals to S 0. So, that is what you can do, you can write down again all these S in terms of the Young diagrams, hook numbers and all these.
Large n, you said that you get the vacuum.
This is not vacuum.
S00
S00 is your partition function. Okay, partition function of Chern-Simons, pure Chern-Simons theory on S3. These two.
insertions or
There is no, here there is no insertions.
no insertions.
Right.
And then you are taking large n limit of that answer.
Yes, so this is in a different framing because I have done some different modular transformations.
I can see, yes.
Okay, but the point is that these two quantities are same up to some phase factor.
Yes.
Okay, you can do the explicit check. You take SU2 level 3. You do the explicit check. You can see it.
And what was large n?
Large n means, so what I expect in large n I expect that a particular representation will dominate, all other representations will be suppressed by 1 over n square factor or 1 over n square factor. Okay. So, therefore, in the large n, this combination evaluated on that particular representation should be equals to S00.
S00 is what is S00?
S00 is that S matrix I have calculated for identity representations. Right.
I thought this is if you take exact expression for S00, like at finite n and finite k that is available.
Right.
Then the partition function in Witten's framing, I don't know what it is.
Yeah, whatever,
In
canonical.
Witten's framing, that partition function even at finite and n and k it
Is
is
S0, you know that partition
Why do
function.
you need to take large n to see this?
Oh, okay.
No, it's replacing sum over r with a single r.
Sum over, I am replacing sum over r by the dominant r.
Dominant r. But why is it that which r dominates telling you something physical the way it did in the earlier case?
Yeah,
Seems
this way of writing it will give you a partition function for, I mean matrix model for Chern-Simons theory on S3.
But this answer is true even at finite n.
This answer is no. For finite n, you have to take sum over all possible representations.
He has the answer at finite n,
This,
taking a large n limit, and then he gets one dominant representation.
Yes, at this line I am asking, in Witten's surgery, even at finite n and k, if you calculate S3 partition function of pure Chern-Simons theory, it is S00. Is this statement correct? Then the answer that you have at finite n and k, why is it not S00?
sum over r S0 r square T r to the power minus 1 is S00. This is true for any n.
Okay,
This is true for any n.
in n. And okay, so the first line is already S00.
Yes.
Then why do you need to take a large limit?
In the, I don't. I mean, this way of writing will give me a partition. A matrix model for Chern-Simons theory. What I am trying to check is that this is a basic check. I will come to you what I am writing the partition. Why I am writing the matrix model. But if I write a matrix model in the large n limit, what will happen? One particular representation will dominate the partition function, and then it has to be true. This is my argument. Okay. So, you do this thing, you write down the partition function, okay. You again do this, define these theta i's which are written in terms of h i's. And one thing which is little different from S2 cross S1 is that now you can see the potential is theta I square, which is not periodic. For S2 cross S1 I had a potential which is cos theta I.
You are working in which gauge? You are working in covariant gauge?
Covariant gauge. Well, here what is that gauge? I mean,
Sorry, if
this is just I am using the
you are not calculating it independently. You are
no,
taking from
right,
S2 cross
right,
S1.
yeah.
Sorry,
So, to write down a unitary matrix model, what I have assumed that
Wait. So the sine square is the s square factor, and the e to the something is the t factor.
e to the power something is coming from the t factor. Okay. So, here I have assumed what we have to do, that this theta I square is not a periodic. So, I have to impose the periodicity condition by hand. Okay. So, I have to repeat this potential beyond theta goes to minus pi and plus pi. So,
and the map between theta and h is the one that you had before.
the map between theta and h is the map what I had before.
So you converted that into a matrix model.
Yes,
Okay.
but here one
I see,
important,
but that seems, so it just seems, it starts looking like a matrix model.
right, but the potential is not periodic.
Yeah,
But again, the same, since my theta i's are again hi, so again my eigenvalue distributions are again capped.
yeah.
So you can find the, in the large n limit, you can find, solving the saddle point equation, you can find the distribution. This is the distribution. This is a one gap distribution because there is minus pi.
That had to happen. The answer should look like a unitary matrix model.
At least the measure factor you are getting.
Yeah, but is this some miracle, or was it expected?
This is I mean this theta, this potential sum over I theta I square, sum over I theta I square. This you can write minus 1 whole to the power n by n square raise u n plus raise u dagger n sum over n. This theta I square potential you can write as an infinite placket model. Okay. This also people have done this. People have written the Chern-Simons matrix model. I think Okuda maybe. You can Calabi crystal paper.
So you can derive this directly from.
You can derive that directly from.
So then the next question stands. What is the gain from?
Okay, that I do not know. Yeah. What?
No, you can derive it.
No, not from this is for S3. This is the partition function for S3.
Usually people do localization covariant values.
Yeah. Anyway, yeah. So, but one thing we encountered here is little surprising, which we didn't understand the meaning yet, because you see the free energy for the partition function I know exactly. It's because it's a S00, right? And I know that there is no phase transition, nothing. It's a topological theory. But here we see that there is a lambda value at which the eigenvalue density touches the 1 over upper cap. Okay. So, this is the corresponding lambda value. Okay. So, which means that the large n representations I am considering may not be an integrable representation anymore. So, somehow we are encountering this lambda star value where we see that eigenvalue distribution saturates the upper limit 1 over 2 pi lambda, and after that the eigenvalue distribution goes beyond 1 over 2 pi lambda. If I just neglect that cap on the eigenvalue distribution, if I just calculate free energy for this solution, the free energy I get will match with S00. There is no problem with that, but somehow I can see size there exists some lambda star where this eigenvalue distribution will touch the 1 over 2 pi lambda, where actually what is exactly the upper cap which is coming from the discretization of eigenvalue. If you calculate free energy for this distribution, you will get the same free energy S00 in the large n limit. Okay. Yeah, this is little annoying, which we haven't understood too.
Because in your previous form, in terms of the representation, manifestly had integrable representations in it. So at large n, one of them must dominate.
One must dominate up to from 0 to lambda star, it is fine. All the representations are done.
Does that mean that the map is now not quite?
Something we haven't understood. We are. Another thing is that one can cook up some two gap phase in the Chern-Simons theory. In fact, this was also shown by Morita and Sugayama. In fact, they showed that there exists a multi-gap phase in Chern-Simons theory, not just two gap phase. There exists a multi-gap phase. So we just consider two gap phase, which is given by this, and in this two gap phase there is a parameter gamma sitting which you cannot fix by the analyticity condition of.
But what are these different phases are for? Like they are giving same free energy or not?
That is what I'm coming. So I have this two gap phase, okay, and I have this extra parameter gamma. Okay. So how I find this two gap phase? I find this, I define my resolvent and demand that my resolvent is analytic inside in the complex plane. So from that analyticity condition I couldn't fix this gamma, but you take this eigenvalue distribution, it satisfies rho theta d theta equals to 1 as well as it satisfies the eigenvalue equation. So this is a bona fide solution of the saddle point equation. There is a gamma floating here, my free energy will depend on gamma. I can choose some gamma such that the free energy corresponding to this two gap solution and the one gap solution are same. Okay.
Can you get a better free energy by tuning gamma?
No, I'm better free energy in the sense?
Dominant free energy.
Yes, you can, but I do not, I mean this is something we are not understanding.
So
This
the
is-
free energy has to agree with as log as 0, 0.
Free energy has to agree with S00. Free energy is given, but I can cook up a two gap solution with some gamma. Okay. So this is my two gap solution and this red one is my one gap solution, which are the blue line is the 1 over 2 pi lambda, and I can choose some gamma for the such that these two solutions have same free energy.
And you can get a better by choosing, by taking gamma one side of that, you can get a better.
Better free energy. I do not know what is the, is there any microscope
Meaning better matching with decimal three?
No, better meaning dominant over S.
dominant over S0.
Wrong.
So in fact we have done it for two gap because we have done it analytically, but probably you can do it for multi gap also. Okay. So and interestingly that at the same value lambda star, both two gap and one gap they saturate the upper bound. So this is something, the existence of this two gap solution, something we didn't understand well. Maybe we need to look at more what exactly, because is there any kind of microscopic understanding or not, I do not know. So let me just summarize. I think we have enough discussed enough. So this is exactly the partition. We have written partition function in terms of this Weis-Dumino quantities of Weis-Dumino Witten, and from the properties of modular transform matrix you can write down the unitary matrix model. Discretization comes from the Hooke numbers, and we have shown that how these different diagrams, different Largian phases are related to each other by level rank transposition, level rank duality and the transposition of diagrams. And these are the two things we encountered in S3. We encountered some two gap phase which has the same free energy as one gap phase, and we haven't understood the meaning existence of the two gap phase well enough. And some outlook, as I was discussing, using the properties of these the modular transformation matrices, can one say something concrete about the level rank duality for Chern-Simons theory coupled with S2 process 1. Chern-Simons theory on S2 process 1 coupled with different matters and all these things, and of course the understanding the two gap phase in Chern-Simons theory on S3. Thank you.
Any more questions?
Sorry, I'm going to ask an embarrassing question. I missed how you got to the matrix module for S3. You could just very, very briefly tell me. Okay, so that comes from modular. That comes from surgery. That rule.
That comes from surgery.
And then how did you make that a matrix module?
So I use, you know, S0R goes as sin pi hi minus hj by k plus n. Okay, I write all these things. So t is given by number of characters. T you can write in terms of li's you can write in terms of hi's.
These are you're using explicit known results for T and S matrices of
I mean,
Weis-Dumino Witten.
Right.
Okay, fine. And then
Then you plug it. So sum over hi means sum over r means sum over hi's. Then I redefine the variable, and then I write it as a partition as this thing.
Sum goes to integral because of this one.
And is there a cap on the eigenvalue?
Yeah, it seems so because theta is are again hi's.
Because it's again discrete.
Discrete, yeah.
And there's the same van der Waals measure.
Same van der Waals.
Okay, so it's just happened somehow.
Yeah, this
Just
is
happened
good for
somehow.
the